So the last little bit of the equilibrium chapter is to show you how equilibrium is actually related to both kinetics and thermodynamics. The first thing I want to talk about is the connection to thermodynamics, and it starts with an equation that you're going to need to know. The equation is delta G reaction equals delta G0 reaction plus RT ln Q. Now, the thing to remember about that little zero superscript is that that actually means under standard conditions. So delta G0 reaction can be calculated using standard values from a big chart. The big chart that I gave you earlier would actually work very, very well for this. Another reminder would be the R in this particular equation, because now we're dealing with units of energy, would be 8.314. That's extremely important that you don't get that confused with the gas constant 0.08206. In this particular chapter, now we're going to use both R's, so please make sure that you can differentiate between the two. If you are not a natural log fan, if you like to use base 10 logs, there's a difference in the equation. You can actually just use 2.303 RT log Q instead of the RT ln Q if you prefer. It's just a different button on the calculator. I like the equation that's pictured actually at the top of the screen the most. Now, one important thing we did talk about before was that at equilibrium, the overall value of delta G actually equals 0. Q, we've actually talked about in this chapter, that refers to a reaction quotient. If you are at equilibrium, your value for Q should be the same as K. So now there's a couple things that we can actually substitute back into this equation only when we're dealing with an equilibrium type system. I popped a 0 in for my delta G value, which might make things a little bit interesting, and then I also substituted a K instead of my Q. We're going to go through and simplify that equation, and now you can see that delta G reaction equals negative RT ln K. So now this gives you a really quick and easy way to calculate an equilibrium K value if all that you have to go with is thermodynamic values. So from delta G, you can actually calculate this, which is really kind of cool. Please also remember that you can actually get your delta G value in a variety of different ways. You can do that from just plain old delta G values that are listed in a thermodynamic table, or you can actually get that using delta H and delta S values. You might want to go back through, look over your notes on this particular section, because you are going to have to be using that in a variety of different ways. Also, to be clear, K is just a generic K. You've got to look at your state symbols very carefully to make sure that you're dealing with either a gaseous system or more of an aqueous system to determine whether or not what you're calculating is a Kc or a Kp. Now, K also changes with temperature. Just like it did in kinetics, it also does this in equilibrium. Now, we had a very interesting little equation that we used in kinetics. Maybe you remember it. We called it the Arrhenius equation, and I'll show that to you here. Now, remember that that was the natural log of K1 divided by K2 equals negative EA over R, and that's the 8.314. And then multiplied times all of these cute little fractions subtracted from each other. 1 over T1 minus 1 over T2. Now that works for kinetics, but there's something you need to kind of keep in mind, and potential energy diagrams will help you kind of understand the difference between the kinetics equation versus the equilibrium style equation. So in a potential energy diagram, you need to remember that most kinetics type experiments are really only a one-way, one single direction type pathway, where you only ever start with reactants and you go to products. And now remember, as part of that equation, you're being able to calculate or maybe even insert into that equation the activation energy. Now, the difference here in equilibrium is that our reaction can actually travel in both ways, from reactant to product, but also from product to reactant. So not only do we have an activation energy for the forward reaction, but we also have activation energy for the reverse reaction as well. If you subtract those two, you get an entirely different value, and that would be delta H. So now, I think you might be able to figure out how our equilibrium version of the Arrhenius equation is a little bit different. I wanted to kind of put these two things right next to each other. So the original Arrhenius equation, which you now know and love, has activation energy as part of it. However, in equilibrium, that term changes to delta H, the overall heat of the reaction, which can also be calculated through thermodynamic values, so please make sure that you're able to still calculate those. This equation now grows into a different name, and we call it the Van't Hoff equation.